Hi everyone! So for this video, we're actually going to go back and think a little bit about an actual biological model. We've been spending some time talking about stability of just abstract difference equations, nonlinear difference equations. But now today we're going to talk about the approximate logistic equation, which is one of the super well-known population models. So now, suppose we introduce an organism into an environment. An organism. You could give it a name if you want, but that's not so important. So what happens? So initially, if this organism is something that is fit and so it reproduces, initially it might reproduce exponentially. So might reproduce exponentially, because every organism that's there is going to reproduce some number of copies, but eventually uses up the available resources. Uses up available resources, and it's no longer able to grow so fast, at which point the growth slows down. So what does this look like? Well, if you might have an exponential curve, and then you might think, well, at some point it's going to slow down, and so then maybe you have something that looks sort of like a reverse exponential curve up here. Let me give myself some more space. So you might have maybe that's an exponential curve, but then maybe at some point around here it starts slowing down, and so you have that instead. Let me draw this separately. So maybe initially you have an exponential curve, and then at some point it slows down. Okay, so you have some initial exponential growth. And then it slows down. And let's assume that there's some maximum number that the population, so this here is the zero line. Let me put that in, what color? Let's put that in blue. And then let's suppose that we have some carrying capacity. So, which is the maximum number of individuals the population supports. So now, this is one thing that you might imagine being modeled by this. So you could think of this as a super simple disease model, for example. So if you were to introduce some new respiratory disease into a population that has no resistance to it, well, initially you might reproduce exponentially, and then as time goes on, you might start running out of available hosts, and then it starts slowing down. Though, of course, by that point, it spreads to nearly all available hosts. Or alternately, maybe you're introducing rabbits into a place where there aren't any rabbits at all, and if the rabbits are fit, well, they'll breed like rabbits, and then all of a sudden you have an exponential number of rabbits until they eat all the available food, and then those things will start slowing down. So your population starts slow, grows exponentially, and then slows down near the top. And so this is characteristic of, so this thing sort of looks like an S. And so this is something we call a sigmoid curve. And now, this is all really heuristic, but let's actually write down the differential equation. Not a difference equation, a differential equation, which is going to be called the logistic equation. So we have dy dt. So initially, we want it to be the rate of growth to be basically equal to some constant times the population size, right? So this is an exponential growth curve. If you were to, this was just the case, then it would grow exponentially up until infinity, to infinity and beyond. But now, in this particular case, we want it to slow down once you start getting close to a carrying capacity. So we're going to multiply this by a term 1 minus y over k, where k greater than 0 is the carrying capacity. So once you get to k individuals, then your growth rate slows down to 0. And so you tend to approach this exponential, approach that asymptotically as you get closer and closer. Okay, so this is what we call the intrinsic growth rate. Intrinsic growth rate. And let's actually put this in red just to match everything else. Okay, so we have this intrinsic carrying capacity, and so this is the logistic equation. Let's call this. This is the logistic equation. And it's a differential equation, which some of you might have seen before, especially if you've taken any sort of modeling or ecology class. Now, we're going to discuss this logistic differential equation later. But for now, let's try to approximate it instead. We've been learning all about difference equations in this course. And so we haven't actually studied the tools of differential equation in this course. And so instead, let's try to approximate it by discretizing it. And this also is going to be an illustration of sort of interlinks between difference equations and differential equations. As I mentioned in the very first day of class, you can sort of go between them with some amount of loss, obviously, since you're doing an approximation. So for now, let's approximate the logistic equation. Let me be specific. The logistic differential equation via a difference equation. So to do that, we're going to have to approximate, and we're going to have discrete time steps, right? So let's think. So dy dt, that's approximately equal to y of t plus delta t minus y of t divided by delta t. So that's just the baby calculus version of what a derivative is. And obviously, as delta t goes to 0, then that is one way of defining the derivative. And so that's the instantaneous rate of change. Whereas here, because we have this delta t, if that's some finite length of time, then it's not instantaneous. It's the amount of change over some period of time. So this is an approximation we can use. And of course, this is equal to a y of t. So these are all just y is a function of t and nothing else. So we're setting that equal. And if we rewrite this a little bit, this ends up being y of t plus delta t is equal to y of t plus a delta t y of t times 1 minus y of t divided by k. Okay, and so this is for some time step delta t. So let's assume that delta t is equal to 1. Delta t is equal to 1. We're just going to define that to be the length of a time step, so you can change your units to make that the case. Well, then what do you get? Well, then you get that this here is y of t plus 1 is equal to y of t plus a, delta t is just equal to 1, so we don't need that, y sub t again, and 1 minus y sub t over k. And if we rewrite this a little bit, this is equal to 1 plus a times y of t minus a y of t squared over k. And so again, we still have this exponential growth parameter. And we have a limit to the population growth over here. So limit to population growth dependent on density, on something called density. So basically, how dense are the number of individuals in our population? And when you have too many of them, well, then the population grows more slowly. Now, note that this has a couple different variables, right? We also have this carrying capacity variable here. That's still there. The k. And so we have two different parameters that control this approximate logistic difference equation. We can lump the two of them together by doing a change of variables, and that's going to make our analysis a lot easier. So let's change variables. Let's say that x sub t is equal to a y sub t over k times 1 plus a. And we're going to say r is equal to 1 plus a. Well, then when we do that, you end up getting that x sub t plus 1 is equal to, well, let's plug that in. A over k times 1 plus a times y sub t plus 1. And y sub t plus 1 we can plug in our above equation in. So that's going to be equal to a over k times y sub t minus a squared over k squared 1 plus a y sub t squared. And that's going to be equal to a y sub t over k times 1 minus, and this here is a y sub t over k times 1 plus a. But of course, that entire thing is just equal to x sub t, that fraction inside. So this is a y sub t over k times 1 minus x sub t. But a y sub t over k is also just equal to 1 plus a by substituting the variables. This is equal to 1 plus a times x sub t times 1 minus x sub t. And we also set r equal to 1 plus a, so that was our other change. And so this thing is equal to r times x sub t 1 minus x sub t. And this is x sub t plus 1. And this here is the dimensionless form discrete logistic equation. Sometimes it's called the dimensionless form discrete approximate logistic equation because we have approximated by discretizing into time steps of finite time. And note, the important thing here is that we have only one parameter now, one parameter r. So this is a lot easier to analyze. And now the next thing we'll do is let's assume let's ensure that things are non-negative. Ensure things are non-negative. Non-negative. Because you can't have a negative number of rabbits in your environment or a negative number of coronavirus cases, as much as we would like that to be the case. And so, because we're in a mathematical biology class, let's restrict our initial conditions and our parameters so that the solutions are non-negative. So, assume that 0 is less than r is less than 4, and 0 is less than or equal to x naught is less than 1. And so what we'll see is that we basically, in doing this change of variables, we basically restricted everything to be between 0 and 1, which is nice because then you can just think of everything as a proportion of the maximum possible, depending on how you're thinking about the difference equation. Okay, and so one of the things that you'll notice is that in our difference equation up there, we had f of x is equal to rx times 1 minus x for the standard form of nonlinearity of the difference equation. And so then max over x in 0, 1 of f of x turns out to be f of 1/2. I'm not going to compute this in class, but that's something you should be able to verify using simple calculus. And so that's why we chose our values. We chose r is greater than 0, less than 4, because if r is greater than 4, then f of 1/2 is greater than 1, and f of 1/2 is less than 0, and then becomes negative. So we need that. So that's why we have these bounds on r. Also, we don't want to start out with a negative number, and it turns out that by choosing these parameters, so by choosing 0 less than r is less than 4, and 0 is greater than or equal to, x naught is greater than or equal to 0 is less than 1, f happens to go from 0, 1 to 0, 1. which is a very nice range to work with. Also, note that f of 0 is equal to f of 1 is equal to 0. Okay, so the function starts and ends at 0 in our domain from 0 to 1, basically. And with a little work, can show the equilibrium solutions. Find equilibrium solutions. X bar is equal to 0, and x bar is equal to r minus 1 over r. And once you have this, we can do a stability analysis. So let's start with a local stability analysis, since that's a lot easier to characterize, and you basically just have to look at the derivatives using the various derivative tests. So if 0 is less than r is less than or equal to 1, well, then x bar is less than 0. So 0, is less than 1. We have that x bar is equal to r minus 1 over r is less than 0. So 0 is only non-negative fixed point. Okay, well, and then how do we figure out whether it's stable or not? Well, f of x is equal to rx times 1 minus x. F prime of x is equal to r minus 2rx. And f prime of 0 is going to be equal to r. So 0 is a locally asymptotically stable fixed point. Okay, because we know that r is less than 1, and so of course the bigger than 0, and so of course the magnitude is less than that. Sorry, let me actually make this strictly less than 1. Because if it's equal to 1, then of course the first derivative test doesn't actually tell you whether or not it's stable there. Second, if 1 is less than r is less than 4, both x bar equal to 0 and x bar is equal to r minus 1 over r are positive fixed points. Now we have two fixed points instead of just one. So f prime of 0 is equal to r is greater than 1, so 0 is now unstable. F prime of r minus 1 over r is equal to r minus 2r times r minus 1 over r, which is equal to r minus 2 times r minus 1, which is equal to minus r plus 2. Okay, so once that's the case, r minus 1 over r is stable when 1 is less than r is less than 3, and it's unstable when r is greater than 3. And this is all just by using the first derivative test. So now, these changes in, let me just go ahead and mention this. Actually, let me call that an aside. Will be aside. This change in stability as our parameter changes at r equals 0 and r equal to 3 are called bifurcations. And we're going to be studying this in the next set of videos for Thursday. So these are called bifurcations, which we will discuss next time. We'll discuss and analyze next time. One other interesting thing to do, which we'll also be doing in this class, is I might also ask you questions about the global stability of these fixed points, which from the last set of videos you now have the tools to analyze. Well, thank you very much, and I'll see you in the next video.